We're going to be taking a look at a frequency doubled vanadate. This particular laser, put that back in, put this up here. This is this laser that we're looking at is the Verde. It's manufactured by Coherent. It's the V10, which is the 10-watt version. Coherent certainly isn't the only one that makes this type of laser. The next manufacturer that comes to mind is Spectrophysics. Their model is the Millennia. So if you're looking at a Millennia or doing an analysis on a Millennia, it's going to be almost identical to the analysis we're doing here for the Verde. This is a very common laser in research as it is used as the excitation mechanism or pump source for titanium sapphire lasers, which are very useful tools in research. They have an output that is tunable over a wide range of wavelengths, and if you run them in the pulse mode, they can give you ultra short pulses. So yeah, a very useful tool, TI-SAFs. The other industry that you see this type of laser is the laser entertainment industry. If you're doing something outdoors or in a big space like an auditorium or outdoors, this is a very nice laser to use because it has very good beam propagation parameters and it has high average power. And of course, it's invisible so you can see it. Yep, and that's why you would use it for a laser special effect, right? All right, so let's get started. It is the output wavelength is 532. The average power is 10 watts. It's continuous wave. We're going to be using the ANSI default exposure duration for an accidental or unintentional exposure, and of course that is a quarter-second exposure duration. We'll be using 1 over E squared. Of course, if that's not given, we always pick 1 over E squared versus 1 over E for a given set of parameters, beam propagation parameters, because it gives us a more conservative result. The spatial profile is circular Gaussian. The beam diameter we're using is 2.48. Now I know the manufacturer's spec sheet said 2.25, but it was plus or minus 10%. And since we would like the most realistic conservative case, we know that for a given beam diameter at waist and a given m squared value, that the larger diameter at waist will calculate a smaller divergence, which gives us a more conservative result when we're calculating like our NOHD. So we take the 10%, add it to the 2.25, we round up, that gives us 2.48 millimeters at the beam diameter at waist. Then we're going to use m squared to see what the divergence is if we use the m squared of 1.1 that is given. Now m squared is referred to as a beam quality factor. It's really a beam propagation factor. Beam quality is subjective and it's about the application. So for example, good beam quality for cutting is not being good beam quality for welding or heat treating and vice versa. So beam quality is subjective. It's based on the application. So a better way of looking at m squared is it's a propagation value. It tells us that for a given beam waist diameter and a given m squared, we can calculate the lowest divergence possible, theoretically possible, for those two given parameters. And so even though the manufacturer spec sheet said, well, you have a divergence of 0.5, we're going to look at the various combinations to make sure we come up with the most conservative case. And for the specifications given on the Verde data sheet, this is it. We'll use the m squared of 1.1. We'll up the beam diameter from 2.25 to 2.48. That calculates a divergence of 300 microradians. And that is less than the 0.5 milliradians, and that's probably the reason on the spec sheet they say it could be less than 0.5 milliradians is because if you use the m squared and the beam diameter is at the high end of the tolerance, well, you would get a lower divergence than a half a milliradian, right? Okay, and that's kind of what we've set up here. We can see that the beam diameter at the observer range of a half a meter is just a bit over what we start with at the waist, and that's because we're not, of course, we're not looking very far down the propagation path. This gives us an OD at observer range of 4. Worst case is 4, and that's because the transmission through the limiting aperture at the observer is 100% through the limiting aperture of 7 millimeters. So the worst case NOD at observer range will be the same. The NOHD is about 3.34 kilometers, or a little over 3,300 meters. The NOHD isn't that important to us in a laboratory, but if we're working outdoors, it's very important to us because we want to know how far this beam could potentially propagate and still be a hazard. Now, as far as calculating the NOHD, we always do it, even for a laboratory situation, because it does give you an idea of how hazardous this beam may be. Okay, and let's take a look at the NSHD, and we'll see it's just a touch over 94 meters. What's really driving the difference between the NSHD and the NOHD, of course, are the MPEs that are associated with both the NOHD and NSHD. So the MPE, the ocular MPE, is 2.55 milliwatts per square centimeter. That is our MPE that most of us tend to remember for visible wavelength quarter-second exposure. The skin MPE is far less restrictive. It's 3.11 watts per square centimeter. But look at the times skin MPE. This is telling us how much over the MPE is the irradiance of the laser. And let's just review how that's calculated in safety. We look at the power transmitted through the limiting aperture, and in this case that's the 10 watts. So that's being transmitted through the limiting aperture, and then we divide that power transmitted through the limiting aperture, we divide it by the area of the limiting aperture, and that gives us the irradiance of the laser that we're going to be using here. And the reason we use the limiting aperture is that's because, well, the tables are normalized to using limiting apertures, so that's how we calculate the irradiance for the laser. Excuse me. All right, so we have the irradiance of the laser here. It's 26 watts per square centimeter. It's compared to, in the case of the eye, the ocular MPE, and you can see that they're almost identical, except for, of course, the exponent and the +1 and -3 that says we're 4 orders of magnitude difference, and that shows up right here in our OD. Now, let's get back to the skin. We can see the times skin MPE, the irradiance of the laser, which is the power propagated through the skin limiting aperture, which is 3.5 millimeters. That gives us a area of the limiting aperture of 0.096 square centimeters. And we don't report how much power is passing through that limiting aperture, but that irradiance is calculated and then compared to the MPE, and we can see that in this case the irradiance of the laser through the limiting aperture for the skin, or using the limiting aperture of the skin, is about 33 times above the MPE. So is this laser a skin hazard? Absolutely it is. It's what I would consider a pretty severe skin hazard. Okay, if you stick your hand or arm in this beam, it's going to really hurt. If you put a piece of wood in front of this beam, a flame's going to pop off of it. So if you can light up a piece of wood, it's going to light you up too. So you don't want to do this. Now, if you do get your hand or some part of your skin exposed to this laser, it's certainly not going to be a something you can't get over. It is going to give you something that you will remember and you won't do it again. Okay? All right, so that kind of tells us what the MPEs are, the time skin MPE, the ODs. Let's take a look at the diffuse reflection hazard. Now, we are in the retinal hazard region, so we will have a source type, either point or extended. In this case, we have a small beam on target. We've left that observer is 1/4 of a meter. we're using 600 seconds as a default exposure duration because sometimes, as we said, people are exposed to diffuse reflections either intentionally or unintentionally for long periods of time. So we typically put about 600 seconds in here. We can see that the MPE for the diffuse reflection based on this exposure duration is about 1 milliwatt per square centimeter. That gives us an NHZ of 5.61 meters. OD at observer range at 1/4 of a meter is 0.72. That makes sense since we're inside the NHC. And then we can look at the skin NHC, the skin MPE, which is based on this exposure duration. And the time skin MPE, and we can see that the diffuse reflection hazard is 0. You have no hazard from a diffuse reflection. But realistically, this would not be a small beam on the target. It would be probably at least the 2.48. So let's put the 2.48 in, shall we? We'll put 2.48 in. And we can see that we have now something less than what we saw with the point source type. This is an extended source. The MPE has gotten less restrictive. The NHZ is a bit over 1/4 of a meter. And of course, with our observer at 1/4 of a meter, we see a little bit of an OD requirement. But in this situation, being less than 0.1, we would say there's no need for an OD requirement. An extended source, of course, is when the angle subtended from the observer looking back at the beam on target, that angle is greater than 1.5 milliradians. Let's take a look at what that angle is. We can come over here to correction factors and time limits, see where it says interbeam. We're going to click here and get the diffuse, and we can see that the angle subtended, this is in the x-axis and then the y-axis, of course it's circular, so they'll be the same, is about 7 milliradians. This gives us, the alpha effective is an average of the two. And of course, in this case, alpha effective is the same as each individual. The angle in each axis. Okay, I knew I would get there sooner or later. Okay, and then you can see other correction factors here. Here's your blue light correction factor. And then, of course, C sub E is T max, meaning for this exposure duration, C sub E is 4.68. And, of course, we don't have a pulse, but this would be C sub E for a pulse duration if we were looking at a repetitive pulse laser. But since we're not, it's just reporting the same as T max, which is 4.68. And this is one of the factors, of course, that goes into increasing the MPE, making it less restrictive than the point source MPE. All right, we'll set this back. Let's see, one other thing I may want to talk about is, of course, the irradiance in the beam itself. If I was looking at a barrier for this and I was looking, say, my barrier is going to be 1.5 meters away. Then I will set this, the observer range at 1.5 meters because that's what this is working off of. And then I'll set this to 1/E. And I can see that I would need a barrier that could withstand 400 watts per square centimeter at that distance. All right, so I would give that information to my vendor, or I would hold that information and give all the parameters, the input parameters, to the vendor and see if they agree with this particular calculation. All right. Okay, I think that's about it.